Now I don't need to know math. All I need to know is English, and I can start building models. One of the things that we like to think about that Dyad does is make hardware engineering as easy as software. Tools like Dyad are going to be really successful, I believe, in the long run. And it's not just about chasing the incumbents, it's about growing the pie. It's not the $10 billion TAM right now that we see today, it's the $1 trillion TAM, right? I do honestly believe that hardware product engineering is going to become like software.
Welcome to Terminal Value. Today, I'm joined by Viral Shah, co-founder and CEO of JuliaHub. JuliaHub is building Dyad, an agentic platform for physics-based engineering and simulation. The core idea is that designing complex physical products still involves fragmented software, specialized engineering knowledge, and expensing cycles of laboratory and real-world testing. Dyad is trying to change that by combining a physics compiler with AI agents, allowing engineers to build and validate more of these systems computationally. In this episode, we talk about why physical engineering has been so difficult to automate and what an AI agent actually needs to bring to the underlying model, in addition to how the economics of agents change as inference gets cheaper, and ultimately whether hardware engineering can start to look much more like software development. Now, onto the episode. Viral, thank you so much for joining Terminal Value.
Great to be here, Nick. Thanks for inviting me.
Yeah, absolutely. And so before we get into JuliaHub and what you're building over there, I'd love to set the tone for the audience and have you walk through what the environment is today for engineers who have to build complex physical products. Can you walk through what they face today in terms of just their process from the initial requirements all the way to getting a simulation model that they trust?
Yeah, so this is in the world of engineering. I mean, this is a little bit old and has been around for a while. It's called the engineering we, and I have this screen share on which I'm sharing this with you. So in the engineering we, imagine you're starting out with I want to build this product. Let's say I want to build an aircraft that flies such and such distance. These are my fuel budget targets. These are my cost constraints. This is the cargo I want to carry. These are the number of people I want to carry. Whatever be your requirements, right? So you start out with a bunch of requirements, right? That's what every product starts with, the product requirements. And then the way the weave works is you start out all the way at the top with the system requirements, and then you kind of cascade down. Okay, so from the individual system requirements, you get system design, and you get component level design, subsystem level design. So you iteratively start from a very high level set of requirements to decomposing them into all the different systems and subsystems, all the way down to the component, right? So, like if I'm building an aircraft, what are the requirements for the aircraft door? What's the requirements for the windows? The requirements for the lavatories, for the seats, right? For the flight control system, for the cockpit. Like every single thing boils down into a set of requirements and then all the way down to the component level. And you build models for each of these different systems, subsystems, and components. And eventually, that's how you go down the V, right? So you're kind of think about it as double clicking all the way down. Mm-hmm. And eventually you have models for everything. You start sort of integrating them back up and testing and verifying them. So once I built a subsystem, I'm gonna, and I have a model for it, I might now have a physical part, I might have data, I might have simulations, and now I'm gonna take those results and integrate them. And then I'm gonna go sort of, zoom back out, integrating all those results from all the models and simulations and seeing if the final product in simulation meets all the requirements that I set out with. So that's your design V, right? So you're zooming in all the way down, building models as you go, and then you're zooming back up, doing verification and validation as you zoom out. Eventually, you're going to operate the product, right? And then comes the issue of operational support and predictive maintenance. That I have this plane, it's flying through. Now I'm an airline operator. I'm flying this plane through different kinds of environmental conditions, and that changes the maintenance schedules and all the planning that goes into keeping that asset running and in good health. So there's a whole set of tooling around building a product, and then there's a whole set of tooling around operating the product. And often, the OEM that builds it is very different from the operator that's going to operate it, and often there what they want out of these things are sort of at odds with each other. But broadly speaking, this is the process.
I see. And you hit on the point of you kind of have to go down the stack, really double click in and then finally go up. Could you walk through along that V process? What are the tools that folks are using, traditionally?
Yeah.
And where are kind of the breaking points today that have kind of caused you to eventually build what you guys are building over at JuliaHub?
That's a very good question, right? Because that kind of goes to the heart of why we started building Dyad, and why we built it on top of Julia, right? So if you look at this V diagram, every step of this is a different software tool that operates in its own silo, that doesn't talk to the other tools. And we've seen engineers kind of operate a tool and then like literally use Excel to punch in values from one tool to the other tool. Often there'll be file exchange, like people try to use all kinds of integrations to have these different tools talk to each other. But at the end of the day, why should there be so many tools, right? And could you have fewer tools? So system requirements, for example, often for many products they're in Excel. If you're someone like a Boeing or an Airbus, maybe you use a tool like Doors, which is a database of requirements. um, um, Increasingly, there are tools that are built around the SysML standard for requirement specification, which use some form of modeling and diagramming for capturing requirements in a more of a sort of machine readable way. Um, However, when you go into sort of the system, subsystem, and component level design, the tools that you use are what are often called 0D or 1D tools. And when you say 0D or 1D, that usually means that it does not take the 3D geometry of the real physical world into account yet. It's just focusing on the system level, or the subsystem level view. So like my power system, my flight control system, my environmental system in an aircraft. And I'm just going to use aircraft as an example because everyone's familiar with it. Everyone's flown in one, and those are some of the most complex things ever designed. So each of these different systems then is modeled. Often these 0D, 1D tools are compilers under the hood. So systems like Modelica, Simulink, AimSim. And Modelica itself is an industry standard, so there are multiple implementations like Daimola and Wolfram Systems Modeler and so on and so forth. But these are usually some of the tools that people use for the system design phase. Now, even in the system design, there's sort of two parts to it. There's what I call, or rather what the field calls, building a plant model, which is I need to simulate all the physics of the aircraft. So like I'm looking at the way the aircraft's flowing through the wind, and how do all the different flight surfaces interact with the flight envelope. And then there are the control systems, which is given sort of where I'm in my flight path, like what do I need to do? I'm taking off, I'm ascending, I'm in cruise control, I have an autopilot engaged, I'm landing, and you have all these different flight surfaces and that's your flight control system, that you have to actuate all these flight surfaces while you're in flight to sort of go through all these different phases. And so you have to design a plant model, which is the physics of the aircraft itself, and then the control system, which is how do you sort of interact in the real world, and then the software that drives all your controllers. Because at the end of the day, when the pilot presses a button, there's a bunch of software that's going to run, that's going to pull down the landing gear, engage the braking system, move the ailerons, right, and all of that. So there's different parts to the system and subsystem level design, which are around building the plant model, around building the controller, and building the software. But eventually, as you zoom in further, you go all the way down to the component level model, right? Like I'm building the door of my aircraft, I'm building the landing gear, and I need to actually have a CAD model of the 3D geometry of that I'm building, that I'm modeling, right? And then I need to analyze it for stress, right? Like is this landing gear, when it actually touches down with the force, that forces that are expected during takeoff and touchdown, like where is the mechanical stress gonna show up? What are the breaking points, right? How much friction is it gonna create? Is it gonna be able to withstand thermodynamical stress, right? And all of these kinds of things. So you often go down to detailed 3D models, right? And you might do finite level element analysis, or you might do Increasingly, people are hoping that inference-based methods using AI tools are going to replace complex FEA methods. But you want to do some kind of detailed 3D simulation to answer all the questions around safety, around structure, around heat, and your cooling systems. All of that that has to come together. And so these are sort of all the different tools. Now, in the component level analysis, you have tools from companies like Ansys, Cadence, Synopsys, Siemens, Dassault Systems, COMSOL, and all of these companies sell a variety of different tools for different physical domains, right? So there are different tools for structural. So you have tools like Ansys Mechanical. You have different tools for heat. You have different tools for fluid dynamics. So like tools like Fluent or Star CCM from Siemens, for example. So there's just a variety of different tools in all these different areas, and each industry sort of has its own tools, right? So for example, if I'm a jet engine developer, I have different tools for modeling combustion. And if I'm a civil engineer focused on building a data center or a high-rise building, I have different tools for structural, and integrity of my structure. And that might be a tool, maybe like Nastran, for example, and so on and so forth, right? So there's just a ton of different tools that people use in modeling and simulation. And then there are sort of tools like MATLAB, right, that will put everything together because you have outputs from the tool above you that need to be fed to your tool, and then outputs from your tool that need to be inputs to the tool that comes afterwards. And you might need some scripting environment. It used to be MATLAB. Increasingly, it's now Julia or Python. So it's really a lot of different tools that go into play when you're building these things. There are different tools for validation, and you kind of have the whole uh, development cycle around model in the loop, software in the loop, and then hardware in the loop before you deploy the product, in the field itself, right? So model in the loop is everything is in software, and then you get software in the loop where you might put some of the algorithms. um, the problem with some of these terminologies is that they're confusing and overlapping, but eventually the goal is to start by simulating everything on the computer to sort of putting everything eventually on the hardware. And the idea is that if you think of the diagram, right, like you're working on a computer, the next step of complexity is you're going to try something in the lab, and the most expensive and time consuming process is trying it out in the field and collecting data, and eventually you're in operation in the real world. And in engineering, we call this idea shift left, right? So if you imagine this diagram going from left to right, what you want is shift left. Instead of the field, you want to do more tests in the lab. And instead of the lab, you want to do more stuff on the computer. And the more simulation tools that you have, the more agentic they are, the more AI technologies you can use, the more you can iterate on the computer, the less you're going to have to spend time in the lab, or the less time that you're going to have to spend in the field itself. And everyone talks about the TAM in modeling and simulation, right? Everyone's talking about the TAM in like, oh, there's billions of dollars of that companies like Siemens and Dassault and Ansys and Synopsys are making, or Cadence, right, in selling simulation tools. But the real TAM is the trillions of dollars that you sort of spend in designing products, which is going to salaries, which is going to laboratory testing, which is going to buying equipment, right, and maintenance and repairs and all of that stuff, right? And the hope is that with all the AI capabilities that are coming out, that not only do we shift left, not only do we do stuff more computationally, but we are actually able to sort of make a meaningful dent in that $1 trillion spend that goes into product engineering itself. So
No, that's a really great foundational setting, and a couple points that I think are really fascinating within that. One is how much complexity there is in the actual process itself to automate or to bring an agent to over time, and two is how much contextualization there is. So it's not simple enough to go bring an agent, but there's a lot of context, down to what type of physical process you're trying to simulate. And so I think it's a really good entry point into what is, if you could describe to the audience, what is JuliaHub, and at a high level, what is Dyad in terms of how does that seek to solve this problem?
So Dyad, so like we spoke about, right? Like there are all these different tools in this landscape, and they're all attacking different parts of the engineering design space. They also operate in different physical domains. So, in order to build any hardware product, like let's take an aircraft as an example, right? You will need an aerodynamicist who's gonna, think about CFD. You're gonna have mechanical engineers that are thinking about the structural safety. You're gonna have people worrying about the heat and thermodynamics. You're gonna have people who are designing the control system for the aircraft, right? So these are teams of hundreds of engineers that usually come together in designing the product. And then, you're gonna test each of these parts individually and separately, and then you're going to put them together and incrementally test them as you put them together, and eventually you're going to have the plane that's going to fly. And as much as we talk about modeling and simulation, if you sort of go back to my point around, like, there's $1 trillion opportunity in engineering, right? The hard part is not in the modeling and simulation world. The hard part is convincing engineers to use tools, because even today, engineers have a preference for, like, hey, let's just rig up a plane together and go fly it and collect some data and see what happens, as opposed to let's design it in software, right? Because software is hard, modeling is hard, math is hard. And to the extent that you can make that easy, you'll find that more of these engineers are going to have a bias towards software rather than a bias towards the laboratory or physical testing. And so the way we've designed Dyad is that it replaces this middle phase out here, right? It connects the system requirements to the component level analysis using agentic modeling tools. As with JuliaHub as a company, one of our really strong suites is that we are very good at compiler design. So we started life by building the Julia language, which is now used by over 2 million programmers worldwide. And then, as Julia is open source, we started out at MIT and is used by all these people. But then as we look at, as we as a company looked at our business, we saw an opportunity at taking our compiler prowess and that we developed using Julia, and applying it to Dyad, which is a physics compiler. So Dyad is a compiler for physics. And the reason why systems design and component level design needs a physics compiler is that you are taking many different kinds of physics across many different domains, right? The thermal domain, the electrical domain, the electromagnetic domain, the structural domain, right? You might have hydraulics, you might have fluid flow, you might have all this stuff that has to come together. And the compiler is the only general purpose computer science tool that can take a variety of disparate physics and compile them into a single simulation and run it, right? As opposed to component level analysis, where you're sort of doing one thing, right? So when I'm doing CFD, I'm solving one equation, one PDE over a very large and complex geometry. But, it's basically, at the end of the day, a library that does it, right? So, or if I'm solving the heat equation, it's a library. And this is sort of where we decided that there is an opportunity in the market, that while, in the PDE solver and the component level, analysis with all those 3D solvers, there's dozens and dozens of software that are out there doing a lot of good work and are trusted by the industry. In the system space, we see a huge gap. We see incumbents like Simulink, which have not really sort of changed much over the last 20 years. We see a huge barrier to entry because it needs a compiler team to come in and earn the trust of the engineer, which can only be done when you've invested 10 years building something like Julia. And one of the reasons why Simulink is successful is because it was built on top of MATLAB, right? And if you look at tools like the Modelica or the AIMSIM ecosystems, they really lack that groundswell of engineering support, or the underlying compiler that really allows you to piece together all these disparate physics. So that's why JuliaHub and Dyad leverage all of our superpowers that we gain from Julia itself and build Dyad, and we sit squarely in this systems design space. And the models that you use for design then also become the models that you use for verification and validation. So these models will then get deployed onto a hardware in the loop system, so that before you fly the plane, you can fly it in a simulator, right? And the simulator is going to have all the all the different IO channels hooked up to your DSpace or OpenRT or concurrent or one of these different Hill systems, and you can take all your models, put them in this flight simulator, and really fly the plane. Not just kind of like a Microsoft flight simulator, right? Because that's not the real aircraft dynamics under the hood, right? What you want is to simulate all the underlying systems in the flight simulator, all the way to that attendant call button, right? When you press that, like what happens? Um, and so that's how all of this stuff comes together, and that's where Dyad plays. So Dyad is, in the systems design, in the verification and validation. An interesting thing that none of the tools do is provide something for building digital twins in the predictive maintenance and operational support part of the life cycle of the product. Because if you think about it, like Boeing's built the plane, right? For example, Airbus has built a plane, but Emirates or United Airlines or Lufthansa, whoever it is, right, is going to operate the plane, or Delta. And what they care about is, I'm going to operate this plane for 20 years, 30 years, and I want to know how my maintenance schedules look like. I don't want to take the plane, I want to replace a part before it fails, right? And so if I had access to the models that were used for design to act as digital twins so that they can be calibrated with incoming data, right, based on what kind of flights did this aircraft go through, right? Did it go through long flights? Did it go through lots of takeoffs and landings? Like, that's going to all decide the life cycle of the different parts, and the maintenance and the repairs and all of that stuff. So a big chunk of what makes Dyad really interesting is that the design models can also be used as digital twins, and all of that is possible because of the flexibility of the system and the really high performance that Dyad brings to the table. Um, and at the end of the day, it's the agent that kind of puts all of it together, right? Because you have engineers who are going to be able to use these tools agentically. Now I don't need to know math, all I need to know is English, and I can start building models. I'm a maintenance engineer using a design tool. All I need is English language and prompting, as opposed to knowing differential equations and solving them, and all this compiler stuff and all these details that go under the hood, right? The agents are a really big part of deploying Dyad successfully in a world which is, in my opinion, 100x larger than the existing business of Simulink and Modelica and AIMSIM.
Yeah, Viral, one of the points that we were talking about a bit earlier before we started recording, but I'd love to dive into here, is the difference between what the agent is doing itself versus where the agent is relying on the context within JuliaHub and within the kind of the Dyad environment. So how do you kind of differentiate between kind of what the model is doing versus when you require the model to call out to a proprietary data set within your own environment?
Yeah, so data sets are always, the hard part of hardware, right, is the data, right? At the end of the day, is the characterization, because it's easy to ask it's easy to ask the Dyad agent today to build a model, to do something, right? Like, that's totally easy to do, but how does that model actually represent the real world, right? And that's the hard part. So that often boils down to calibration, right? So how do you calibrate a model? Well, you need to have experimental data, either from simulations that are realistic or from operating the hardware in the real world itself. So often data comes from component level analysis or detailed 3D models that have been run for, with detailed physics for very, very long periods of time, that are very, very high fidelity. And that becomes sort of input sources for the systems level models, or real life experimental data, right? So one of our customers, for example, is an HVAC customer. And the way they design new HVAC systems is they actually have these gigantic chambers where they can raise the temperature, or they can cool the chamber down to whatever temperature that is that you need. And then you put the HVAC system inside that environment and you test it. And it often takes like on the order of $50,000 a day to operate such a testing facility. And so people will often go out and rent these facilities. It's just like a wind tunnel, right, for an aircraft design, that you need to actually gather data from a wind tunnel at the end of the day with as much as CFD has made all the progress that it has, right? Or if you're, the Williams Formula One team, right, you have to do wind tunnel testing in addition to all the software that you can do. But the hope is that we go down to using more modeling and more simulation so that you need less wind tunnels or less of these thermodynamic chambers. But that's sort of at the end of the day crucial to calibrate your models and make them work. One of our use cases actually, since you mentioned calibration, is this use case. Yeah, so this work that we did for Instron. So Instron is a company that builds mechanical test equipment. So in this case, what you see on the screen is a hydraulic catapult, and this is a catapult that is used to test crash safety for cars. The way this catapult is designed is that it has to accurately mimic all the forces that have been observed in a real car crash with crash test dummies and all of that. And so for every crash test that is done in simulation in this crash simulator, it used to take over a day to just calibrate this machine in order to sort of give you the right right forces, right? And what it was doing was running a detailed simulation saying, hey, if these are the forces I want to observe in real life in my test, then this is the way I have to set up all my hydraulic systems and valves and pistons and everything else. In order to do that, it used to take a day, which means this whole multi-million-dollar machine would sit for a day being unused while this computer was chugging away on the side. We moved it to Dyad, and it's now under a minute. And so that's the kind of stuff that really sort of brings all of these things together. This is how modeling, data, high performance computing, and all these technologies come together to really bring value out of real world product design. And then at the end of the day, they're selling this test equipment to companies that are to automotive companies, right? And they don't want this machine to be sitting idle for a day while it's being calibrated, for example.
I see. And one question I had around that, am I understanding it correctly that there's kind of this balance between really great simulation and the data you collect? And so ideally the simulation is good enough such that you don't have to run as many data collection exercises. Is that the right mental model for this?
Yes. So, what you really want is a library of models that you can trust, right? So that then as you build the next iteration of your product or the next product itself, that you have a set of models you can depend upon and count upon. So think of it's just like software development at some level, right? That, when you build software, you build sort of these individual modules, right, that are well tested, and that becomes sort of your foundational libraries on top of which you can now start building more complex features, and eventually you go all the way up and build your complete product. And the same is true of hardware, right? You want to have models that are very well tested and accurate and something that you can now rely upon as you integrate them into more and more sophisticated pieces of functionality. And you don't want to keep going back and doing those same tests over and over again. So one of the things that we like to think about that Dyad does is make hardware engineering as easy as software. And the hope is to increase the velocity with which hardware is designed just by bringing all the things that we do in software engineering, right? So if you have if you have a hardware design tool that, where the models themselves are represented as text, where you have graphical user interfaces so that engineers can intuitively reason about the design itself, where you have agents that can manipulate the design, that can extend the design, that can incorporate the data and speed up the design process itself. Imagine all of this backed by a simple text file interface, right? Now you've checked that into Git. Now you got, all of this on GitHub with GitHub Actions. You got CI/CD going. So now I have my entire hardware design process beginning to look a lot more like my software development process. And now, instead of sort of, building something in a GUI and saving a binary blob that cannot be easily exchanged or integrated, that, where, one engineer made a change to one subsystem and another engineer was working with a month-old version of it, he did not receive the changes in time. And now they're like, oh my gosh, now we got to go back to the drawing board and redesign everything, right? Imagine instead where all these engineers are building these things, checking everything into Git, CI/CDs running, getting you green check marks as you go along, and you really can speed up the way you design hardware using software methodologies. And we know this with software. And at the end of the day, it's text, it's Git, it's CI/CD, it's agents, right? And all of these things come together. But for that, you need the right compilers, you need the right design, you need the right agentic capabilities, you need the right harness, and that's what we put together.
That provides really great context on the workflow and how Dyad is starting to automate more of those portions, so you can kind of turn this more into software. The where do you find today that which customers are feeling this pain the most? What industries do you guys serve the most today?
So the industries that traditionally have used a lot of modeling and simulation are your traditional aerospace, automotive, defense, right? Um, Semiconductor design, of course, being one of them. So these are our usual areas that we are engaged with. Dyad, at the end of the day, is a general purpose engineering tool. So it is not industry focused itself. However, we build libraries, right? Like, because at the end of the day, it comes out to building those foundational libraries, and those, you need to kind of pick your battles, right, as you go along. So so we are focused on aerospace. Boeing has made an investment in the company. So Boeing is, we're working very closely with them, and as a result, in the aerospace sector, a lot of our product design is focused on safety critical software code generation and meeting the FAA certification, and that's a multi-year process that we've embarked upon with Boeing. In fact, we have one of Boeing's principal engineers going to be at JuliaCon, who's gonna give a keynote on how all of these things come together. We're working with semiconductor companies on analog design. We're working with automotive parts suppliers on helping them improve quality control and manufacturing processes. I spoke about our work with Instron in in mechanical test equipment. We're working with a partner called Binny's, who's a 100-year, which is a company with 100 years of experience in designing water systems. And we're working on building digital twins for water supply systems, for wastewater processing, and for freshwater supply, so that water supply can be uninterrupted, and that the energy that goes into these water systems, is optimized so that you use no more than you need, and that emissions are controlled, right? Especially on the wastewater side. On the freshwater side, it's all about making sure that the pumps don't fail and that you don't lose, service guarantees to your customers. So this is just a small collection of sort of the kinds of industries we're currently engaged with, but it's just tremendous. One of our most proud moments is that, while we're working on the aerospace side to bring, working on guidance and navigation systems, and we're working on embedded software out there. We've also worked with ASML, and in fact, they were one of our sponsors at ASML at JuliaCon in Eindhoven a couple of years ago. And they shared how Julia's in use at ASML. There's over 1,000 users out there, and some of the most complex control systems on their machines are now sort of being written in Julia.
Wow.
So it's kind of, from the nanoscale to the mesoscale, is where Julia and Dyad are playing a big role in now.
Oh, that's fantastic. That's yeah, it's crazy how many different industries you guys are able to consolidate the design process for. That's amazing. So as you think about the customer motion, I'd love to get a sense of how you think about both pricing and as you start to deliver agentic products that are more consumption based in a sense, and how you and the customer thinks about return on that investment when they purchase your solution.
So on the topic of pricing, right? Many of the tools that have been sold today have been sort of sold on a per license, per seat basis. And there's all kinds of complexity around what is the definition of a seat. Like, is it floating? Is it named? Is it tied? Is it geographical? All that stuff, right? And we can sort of think about all the different versions of that. That's what the customers are used to buying right now. However, with agents, things are different, because now you're sort of consuming tokens, and that's variable pricing, right? Because based on the number of tokens you use. So, now the question is, how does this variable pricing work for customers? And this is the part that we are working on with all of our customers, and trying to figure out how it is that it will work out. Because we have customers who want to have their own sort of token generation. They're like, oh, I have my own Anthropic subscription, I'll give you the key, and so I want you to sort of sell me your product on a fixed price basis, on a seat basis, and then I'll sort of eat the variable cost. And there are other customers who are like, I don't know how to do this. I need you to give me a complete solution. But then it's like, oh, wait a second, now JuliaHub as a business has to figure out how to price this. And this is no different than like how companies started working with AWS and cloud before, right? Because so how do you convert the variable pricing into fixed pricing? And I think the world is figuring it out right now. But at the end of the day, we offer two models, right? We have fixed pricing for people who bring their own tokens. They're still going to use our agent, right? Because at the end of the day, it's the harness that drives the value. But our harness can consume tokens from JuliaHub's router, or it can consume it from something else that the customers bring along. And then the pricing would be different in both of these cases. We do offer our product for effectively for free for individuals, hobbyists, and people in academia. So and that includes a pretty substantial amount of agentic usage. So people on the podcast who are listening who want to try it out, just go ahead, download Dyad from juliahub.com, and you're good to go. But for commercial usage, the pricing is evolving, and it depends on which model you're interested in.
Viral, on that point around model usage, because it obviously impacts ROI in a sense, do you find that frontier model usage is critical for your use case, or do you find more and more of your customers being able to access an increasing level of utilization of product with non-frontier models?
Yeah, and eventually what you find is that the differences between the frontier models are not as great as the differences between a frontier model and the harness, right? Using Claude Code versus the Dyad harness itself.
Yeah.
Now, of course, the space is evolving rapidly. Yeah. One of the things that we have found recently that we have not yet published is that the Kimi K3 model gives us, when paired with the Dyad harness, is roughly the same as Opus,
wow,
but at 1/5 of the cost.
That's incredible. So basically the takeaway for me, if I'm understanding this correctly, is over time, as AI gets applied in a much more use case specific manner, it's probably fair to assume that frontier model utilization becomes a less critical factor, and the usefulness of the harness becomes a much more important factor, and then costs come down. So actually, question for you is, do you think in your domain that, because there's this huge debate around, hey, even as frontier model percentage of utilization comes down, there's still going to be a need for it in certain use cases. Do you find that to be true, or do you feel like in the medium term, you'll get to a point where like, hey, I don't know how much better the frontier model is relative to, the best open source model out there? Like, how do you think about that equation in your space?
No, what you articulated makes sense, right? That at least as of today, this field is evolving so fast that it's very hard to say what things will be in 6 months. Like maybe we all shift to frontier models, or maybe open source models are so good we all switch to those. But what we are finding is that frontier models are really, really good at planning, because they have this sort of the whole knowledge of the internet, or all the knowledge of the world in them, right? And they're very good for planning. But then once you start executing on that plan, we find that a lot of the open source models are getting pretty good at the job. Mm-hmm. And you may not need Einstein to sort of build your braking system at the end of the day, right? Like the braking system has been built many times, and when you're building the next model of or the next automobile, like it's not going to be that much different than the one that came before, probably, right? And if you just kind of keep that kind of thinking at the back of your mind, the world is probably gonna evolve in a way where a harness can decide where it needs to use a frontier model, where it needs to use a local model, and how to sort of effectively use a combination in a way where it's low cost. Now, it is also possible that NVIDIA comes up with a breakthrough where there is a lot more RAM and there's a lot more compute in a GPU that can be plugged into my desktop, and I don't need a huge rack of compute to do inference for me. And so imagine that GPU technology 2 years from now is powerful enough to run a Kimi class model or a distilled version of it, right?
Yeah.
It is totally possible. And the you know and the latency that you'll get out of that, right, is going to be phenomenal, right? Like if I can have this thing running locally, and that I'm not thinking about the cost, like of tokens and running all of this, my creativity and my productivity is just gonna go sky high, right?
Yeah.
And but at the end of the day, you need a harness that's gonna make these decisions, right? And so I think at least when you connect these pieces, right, when you bring LLMs into the world of hardware and product design, you need something that's sitting in the middle, that understands the domain, that understands the context, that knows the best of what the models have to offer, and then crafts a unique experience for those users. There's an interesting data point that I wanted to share with you, on engineering and agents, specifically that Anthropic put out. You probably have already seen this, but it's this data set. Um, so this was published by Anthropic, where the top line for each category is, actually the bottom line for each category is the potential for AI to impact a particular field, and then the top line is the current observed one. I think this is about 3 months old at this point, but they kind of go for domain by domain, right? So computer and math and like business and finance, they're pretty high, right? Like the impact is expected to be very high, but we're already observing a significant amount of impact. Whereas if you look at grounds maintenance, well, I mean, that's like the expected impact is low and the observed impact is even lower. But engineering is a world where the expected impact is very high, but the observed impact is very low. And the real reason is because all the companies in this field, your Synopsys, Ansys, Dassault Systems, all of these companies have built real moats in terms of building validated and tested modeling and simulation software that the agents can't just put into a loop, right? Like it's not easy for Claude Code to kind of loop around Simulink the way it can do with GCC or Rust or Go or Julia, for example, right? Today, if you're working with Julia, Claude Code is just fantastic at it. But if you want to do engineering design, it doesn't know what to do. It doesn't know what engineering is. So that's where tools like Dyad are going to be really successful, I believe, in the long run. And it's not just about chasing the incumbents; it's about growing the pie. It's not the $10 billion TAM right now that we see today. It's the $1 trillion TAM, right? Because if you think about engineering, if you think about Apple or NVIDIA, they're literally producing software files, right? And then they email the file to TSMC, which then goes ahead and builds the software. So it builds the hardware and then ships it, puts it on a plane, and sends it back. And so, if you think of Boeing, right, like a majority of their work is in the digital form factor, right? Putting the flight tests and all the hardware tests aside. So all the software part of the work is going to be amenable to AI, which means it's amenable to agents. It's amenable to someone who understands the domain, who's going to be able to consume tokens, in an effective way. And it's not just about cost, but it's about speed of iteration, and it's about solving the problem, faster, better, cheaper, right?
Yep.
And that's where the harness is going to be essentially a big game changer, in my opinion.
I love that. Viral, I got one last question for you. What is one opinion that you have today that is a very contrarian or not a very popular opinion?
I probably need a couple of minutes to think about this. I've generally been someone who's focused all my time and energy on doing contrarian things. Um, so I mean, and this goes back to my own career, but um, post PhD, I had the opportunity to go join Microsoft, and I decided instead to go to India and work on building the Aadhaar platform out there. And everyone told me, don't build a programming language, the world doesn't need one. And working with Jeff and Stefan and Alan, we created the Julia project. And people like every year kept telling us, like, there's no way this is going to get anywhere. Today we're at 2 million users. When we started building Dyad, everyone told us, like, there's no way you can take on Simulink and like companies like Siemens and Dassault. And today, we have a partnership with Ansys and Synopsys, where we're going to market together, with Dyad, right? And we are competing we're competing in this market with all the incumbents that are out there. We're partnering with many of them because they see sort of something that hasn't been seen before. So we, like at the end of the day, I'm sure you know this very well. The startups are built on contrarian views, right? Because if everyone agrees on something, then it's probably already being done, and there isn't an alpha to be captured there. But if you're doing hard things, contrarian things, that's how you stand out, and that's how you make an impact on the world. And I think AI is driving that same thing. It sounds a bit cliched. Everyone's saying this, but I do honestly believe that hardware product engineering is going to become like software, and we are going to shift left, and we are going to do product design a lot more on the computer than we've done in the field and in the labs, and it's going to consume tons and tons of tokens, and it's not going to replace humans, but it's going to be human engineers in charge deciding what to do, and it's the AI that's going to help us cut down those iteration cycles. And so I fully expect that engineering and architecture will will become a lot more like the other fields, with technologies like Dyad, only because of AI and tokens today, right? Like 5 years ago, you could not say, I'm going to try and compete with these giants in the space because they've been around for 20 years, customers trust them, and it's just so hard to compete. Today, the world is open. Like the entry barrier is low. The world is hungry for new technology. Everything's moving rapidly. People want new ideas, new products. They're reinventing the way things are done, and I think this is really an opportunity for hardware design to be reinvented. It's just going to be like writing software. It's just going to be like writing software, as much as engineers do not believe that to be true.
Viral, this is fantastic. Thank you so much for your time today.
Thank you.
That was my conversation with Viral Shah, co-founder and CEO of JuliaHub. My biggest takeaway is that the opportunity is much larger than simply putting an AI copilot on top of existing engineering software. JuliaHub is betting that AI can help shift more of physical product development onto the computer, where physical world models can increasingly be built, tested, versioned, and reused more like software. And what makes that particularly interesting is the role of the harness. The underlying AI models will continue to improve and get cheaper, but Dyad is trying to provide the engineering context, physics, tooling, and validation that let those models actually perform useful work. If that works, the end state starts to look very different from traditional engineering. Text-based models, Git, CI/CD, agents, and much faster iteration before anything ever reaches the lab or the field. The big question is whether hardware development really can become more like software development. If it can, JuliaHub may be going after something much larger than the existing simulation market. Thanks for watching Terminal Value, and I'll see you on the next episode.